Okay. Well, welcome everybody. Thank you for coming. It's a great pleasure today to have with us Dr. Prakash Narayan, who is from University of Maryland. Dr. Narayan received his bachelor's degree in electrical engineering from the Indian Institute of Technology in Madras, and the MS and the Doctor of Science degrees in System Science and Mathematics from Washington University in St. Louis. He's currently Professor of Electrical Engineering and Computer Engineering at the University of Maryland, College Park, with a joint appointment at the Institute for Systems Research. He's held several visiting appointments, including ETH in Zurich, the Technion in Haifa, the Iranian Institute of Hungarian Academy of Sciences in Budapest, University of Bielefeld, LADCB at Padua, and the Indian Institute of Science in Bangalore. His research and teaching interests are in multi-user communication and information theory, cryptography, broadband communication, and network and information theory and statistics in general. He served as the associate editor for the Shannon theory, for those of you who are familiar with the various ethics of the information theory, and is currently on the executive editorial board. He was a member of the governors of the IEEE Information Theory Society, and he's a fellow of the IEEE, and it's a pleasure to have him here today to talk about the Poisson communication channel. Thank you for coming. The floor is yours.
Thank you very much, Hamid. It's a pleasure to be here, and I know Brian and I know Hamid, and it's a pleasure to be here. Thank you very much for the invitation. The Poisson communication channel is a mathematical model for a free space optical communication channel in which information is transmitted by modulating the intensity of an optical beam, such as that from a laser or an LED. 30 plus years ago, my former PhD advisor Don Snyder taught me optical communication, and he taught me point processes, and it is in large part due to his inspiration that I keep coming back to this problem area every few years and try to look at some of the problems that are still open there, and there are many. Kaushik Chakrabarty was my PhD student at the University of Maryland. He is now with Qualcomm, and some of the results that I'll talk about here are based on joint work with him, and they were in fact a part of his PhD dissertation. Praneeth Bodha is a PhD student of mine at the University of Maryland. Himanshu Tyagi was a PhD student. He is now with the University of California at San Diego as a postdoctoral fellow, and he'll be joining the Indian Institute of Science sometime next year as a faculty member. Jianwei Jia and Pritam Mukherjee are also PhD students at the University of Maryland. And Praneeth, Himanshu, Jianwei, and Pritam, they do not work in this problem area, but they were very generous with their time in reviewing my slides and giving me lots of constructive suggestions and criticism. And in fact, Praneeth Bodha is responsible for all the pictures that you're about to see today. I thank all of them. So here is a picture of a generic optical communication system. It's figure 1.1a from a classic book by Karp, Gagliardi, Moran, and Stotz from 1988. And it shows you an information source which the signal comes and modulates an optical source, and the output of the optical source is sent through an optical channel, and the receiver processes the signal, and the photodetected signal is then processed more to extract from it the signal that was sent by the message. This is the basic idea of an optical communication system. I'll begin by looking at some of the benefits of free space optical communication. Now, the technology of free space optical communication has long been motivated by deep space applications. And in fact, these applications provided the impetus for the study of what was known as, or what is known as, communication in the Poisson regime, with some classic papers by Fillmore and Laux, Israel Bar-David, Pierce, and many others. And then with the advent of the optical fiber, FSO, or free space optics, lost some of its momentum. But in recent years, there's been renewed interest in FSO systems, and FSO technology has been proposed as a low-cost, high-rate communication strategy for a number of applications, including metro network extensions, radio frequency wireless backhaul, and importantly, hybrid networks with radio frequency and free space optics wireless components. And there have been a number of creative applications as well, such as LAN-to-LAN connectivity on campuses, inter and intra-chip communication, and questions have been asked as to whether FSO will be critical for LAN connectivity as the Internet of Things develops. And of course, among the benefits of FSO are rapid deployment, high security, inexpensive components, immunity from radio frequency interference, hardly any licensing regulations. And in fact, in January 2009, the IEEE set up a working group to develop standards for local area networks in visible light communication. So the overall larger benefits of using free space optics include bandwidth, spectrum, and security. I would like to mention that there's been a recent development. This is in fiber optics using the nonlinear Fourier transform, in which information is embedded in both the discrete and the continuous spectral components of the Fourier transform. And this is the work by Mansour Yousefi and Frank Kischang, and won the Student Paper Award in the most recent Information Theory Symposium last year. So this, as I said, the hybrid networks with radio frequency wireless and free space optic wireless components are being proposed for a number of applications, and you might have seen pictures like this in different forms. So here's a radio frequency communication tower that's communicating with buildings in a downtown area using optics. In these buildings, all the radio frequency communication is bundled to the rooftops and then transformed into optical communication, and this is how these two units communicate through fog, smog, scintillation, and so on. Similarly, there's communication between buildings using optics, and in fact there's another form of hybrid radio frequency wireless optical communication in which you have parallel links that are both radio frequency and optics, and there's switching back and forth among them. Well, if we would like to use free space optics, of course there are many challenges. So before that, I would say that as we go through, the radio frequency wireless channel is fairly well understood, but the optical channel is not that well understood, and this talk is on the latter. And as we go through the talk, I'll try to draw comparisons between radio frequency communication and optical communication, so you can see what the difficulties are in these two domains. In free space optics, there are very significant challenges. They can be broadly categorized into two groups. The first has to do with mobile and long-range applications, in which there are stringent requirements for pointing and tracking accuracy in acquiring the optical beam at the receiver, and this is because of the narrow divergence of the optical beam at the receiver. The second class of problems have to do with medium and long-range, long-haul links, in which optical fading has to be combated, and this optical fading is due to atmospheric turbulence and link blockage from obscuration due to rain, snow, fog, and so on. And we'll deal with some aspects of this in this talk. The first set of problems has to do with control accuracy and the challenging control problems, but we won't talk about those here. So this is the outline of the talk. The talk will have 4 sections. The first is a basic model for an intensity modulated direct detection optical system. So it's an optical communication system in which a signal is transmitted by modulating the intensity of an optical beam, and at the receiver there's a direct detection device. And in looking at this, I'll introduce the Poisson channel. The second section is binary signaling over a Poisson channel, and we'll talk about the Optimum detector, which is a match filter receiver in the optical sense. And then the third topic will be the Shannon capacity of a Poisson channel. Here we'll talk about the capacity of the Poisson channel and good transmission strategies. And we'll close with the Poisson fading channel, Here we look at the capacity of the single input, single output model, the notion of transmitter power control, and some aspects of the multiple input, multiple output model. So we'll begin with the first topic, which is a basic model for an intensity modulated direct detection optical system. So what is this thing? Here's another picture, and this is from another classic book which came earlier, a book by Gagliardi and Card from 1976. So here is the information signal that has to be sent. It modulates the intensity of an optical beam. The signal is sent through an optical antenna, goes over an optical channel. At the receiver, there's background noise, which is treated as a dark current. The output of this box here is a stream of photoelectrons. And then there is circuit noise, which is typically modeled as additive white Gaussian noise. And for the purposes of this talk, this noise is going to be ignored. And then after this, there's a processor which extracts from what it gets a version of the message signal that was sent. Now, if we look at the optical receiver, this is what it looks like. The received optical field is focused by a lens system onto a spatial filter. In the spatial filter, the spatial component of the optical field is integrated out over the active surface of the detector. So what comes out is a time signal. The frequency filter removes the carrier frequency, and the resulting time signal goes into the photodetector, and then a stream of photoelectrons are emitted, and then the post-detection processor tries to estimate the message signal that was sent from the transmitter. So this is the basic setup. What is a mathematical model for such a system? So here is a basic model. The transmitted message signal is x of t. It's a time signal. It is sent as an optical signal, or here we'll refer to optical. This optical signal has both a time component as well as a spatial component. And the way it looks is as follows. XO of t and r denotes space, is the square root of the information bearing signal x of t. This is the spatial component, and this is the optical carrier. Now the message signal comes under a square root because this optical field, the square of the optical field is called the optical intensity, or the instantaneous power of the optical signal. And therefore the instantaneous power of the optical signal is proportional to x of t, and therefore x of t has to satisfy some constraints. So among other things, x of t has to be non-negative because of the square root. And there's also a peak constraint, and furthermore, the average power of x of t is constrained to be no more than sigma a. I'll come back to these constraints, but I want to note here that these constraints are known as power constraints by virtue of the fact that it is the intensity or the instantaneous power of the optical field, namely this quantity square, that is proportional to x of t. So any constraints that are placed on x of t are referred to as power constraints. The output of the optical channel, if all goes well, is going to be the input. So we'll take it to be approximately the same as the input. Now this optical signal at the receiver goes into a square law detector, where it's squared and then run through a spatial filter which removes the spatial component, and then a low pass filter which extracts the information bearing signal by removing the optical carrier frequency. And then you get a time signal r of t, which if all is well will be the same as the transmitted message signal x of t. So here we'll take r of t to be approximately the same as x of t. Then this is the optical direct detection device, the output of which is a Poisson process. It's a Poisson counting process with a rate lambda t. But before I get to that, this r of t comes here. Lambda 0 is the dark current rate at the photodetector. So lambda of t is the sum of r of t and lambda 0. And this y of t is a Poisson counting process with a rate lambda of t. So y of t has this rate or intensity lambda of t, and lambda of t is the sum of r of t and lambda 0. But r of t was x of t, therefore lambda of t, which is the time varying intensity of the Poisson counting process, it's a deterministic signal. This lambda of t is the sum of the transmitted message signal and a dark current lambda 0. Okay? So this is what happens. And so we observe this y of t, and physically y of t can be interpreted, the jumps in y of t can be thought of as corresponding to the arrival of photons at the photodetector and the corresponding release of photoelectrons, okay, which are then processed. Is the model clear? Yeah? Okay.
So what is, I'm actually not clear about the special component that you're talking about. How does it factor in?
Which one?
The R, right at the beginning, you have XO
Yeah.
of TR.
Yeah.
So where does the...
So this is how the optical, so the signal is multiplicative. So its square root multiplies a spatial component and then there's the optical carrier frequency. So this is what the optical field looks like.
Okay.
Yeah. It is a multiplicative effect. Yeah.
All right,
Yeah.
all right, yeah.
So what's that? R stands for what?
R stands for space.
Okay.
So and
it's a three-dimensional vector.
it's two-dimensional.
Okay.
And then it's filtered out. Yeah.
So since the signal is intensity modulated, we'd assume a bigger jump if a larger signal was sent. Is that the process?
Yeah, so we'll see. We'll see it here. Okay. So the received signal y of t is a Poisson counting process. Look at this picture. This is the Poisson channel. The input to the Poisson channel is the message signal x of t. The output is a Poisson counting process which has a rate lambda of t, which is the sum of x of t and lambda 0. So that's what this says. Right? Now what does that mean? It means that y of t is a process which at time t equal to 0 has the value 0. And for any two time instants tau and t, the number of events that occur between time instant t and time instant t plus tau is a Poisson random variable with a mean lambda, this is gamma, with a mean gamma, where gamma is related to the intensity of the Poisson process. In this way, it's simply the integral from t to t plus tau of the intensity of the process. Okay, so this is the way in which x of t affects y of t. And as I said before, the jumps in y of t correspond to the arrival of photons at the photodetector and the corresponding release of photoelectrons. So that is the Poisson channel. So is that channel clear? So we get now to the next section, which is the most basic form of signaling that we can do over a Poisson channel, namely binary signaling and the corresponding optimum detection for the received signal, to detect the transmitted signal. So here is the problem. There are two signals, x1 of t or x2 of t. Think of them as two possible message signals. They are deterministic. They go into the channel. One of them goes into the channel. And the output is a Poisson counting process, y of t, with rate lambda I of t, which is the sum of the message signal xi of t, which is x1 or x2, plus a dark current rate. All signals are transmitted and received over the time interval 0 through capital T. So I would like to say a few things about notation here. I'm using lowercase letters to denote deterministic quantities, uppercase letters to denote random quantities, but there are some exceptions. For instance, capital T denotes the length of time. Of course, it's a fixed quantity. It can be a variable, but there's nothing random about it. Now, equivalently, the Poisson counting process can be viewed in terms of the random occurrence times of the events. So let T1 through Tn be the observed realization of the Poisson counting process in the time interval from 0 through capital T. Yeah, question?
Is lambda not known to you already?
Which one?
Lambda not?
Lambda 0 is a known constant. It's known. Yeah? Okay. So it's a constant dark current at the photodetector due to secondary emissions, and we take it to be known. Okay? Yeah.
So is the reason for modeling the received signal as a Poisson counting process, is that dictated by how the physics of the receiver?
By the physics of the receiver. That's right. Yeah.
Okay, so this is how the optical receivers are fundamentally different from RF receivers.
This form of direct detection device, there's also a heterodyne receiver, which is of a different kind. So direct detection devices work this way, and they're quite popular in both in free space optical communication as well as in some fiber optic models.
So it's surprising that they have a random response to the input signals.
I'm sorry?
It's just a little surprising that the receivers have random response to received input strength, the strength of the signal. Since
Well, it's a different. So you can have. I'll show you the next picture. So you'll see. Of course, the received signal can be random depending on what was sent. Right? Here, it's a Poisson counting process, and the information is embedded in the rate of the process. And somehow you have to estimate the rate and thereby extract the signal that was embedded in it. Right? So the question here is, suppose that the two message signals were equiprobable. What is the receiver decision rule that minimizes the probability of a reception error? That's the basic question. Now, another convention that I adopt is that whenever a question is framed in single question marks, we know the answer to that question and we know how to solve the problem. If I put 2 question marks on either side, the problem remains open. So we'll use that convention. Now, in order to answer this question, let's look at the counterpart for the additive wide Gaussian noise channel. So this would be a radio frequency channel in Gaussian noise if there were no fade. So this is basic binary signaling over an additive wide Gaussian noise channel. We learn all of this in our classes, and we know what the answer is. There are 2 possible signals, x1 and x2. They go one of them is the input to the channel. The noise is additive Gaussian, V of t. It's wide Gaussian noise with mean 0 and power spectral density n0 by 2. The output is y of t, which is the sum of the signal, transmitted signal, and the noise. Right? And we ask, what is the optimum receiver for equiprobable signaling? And we know that that minimizes the probability of a reception error. And we know that it's a likelihood ratio test, and the likelihood ratio takes the following form. This is the output of a matched filter that is tuned to signal 1. This is the output of a matched filter tuned to signal 2. And this can also be implemented as a correlation receiver. The difference should exceed a threshold. If it exceeds, we say 1. If it doesn't exceed, we say 2. Right? Where this quantity is simply the correlation between y of t and a transmitted signal xi of t. So it's simply the output of a matched filter which is tuned to xi of t. We also know that the error performance improves if the L2 distance between x1 and x2 increases. So the farther apart the 2 signals are in the Euclidean space, the easier it is to tell them apart. The matched filter was invented by Dwight North, and this was in 1943, and it was in a report of the RCA labs in Princeton. Now, by contrast, the analogous problem or the counterpart problem for the Poisson channel was solved 26 years later by Israel Bar David in a paper called Communication in the Poisson Regime. So this was a seminal paper. And here Israel Bar David looked at the binary signaling problem over a Poisson channel and found the optimum receiver. So here let y of t be a Poisson counting process of rate lambda I of t, which is the sum of one of 2 signals, x1 or x2, and the dark current, lambda 0. And all the signals are sent and received on a time interval from 0 through capital T. And let t1 through tn be the random, be the realization of the Poisson counting process. So these are simply the event occurrence times in the interval from 0 to capital T. And what Israel Bar David showed was that for equiprobable signaling, under the probability of error criterion, the optimum likelihood ratio test takes this form. So this quantity here is compared with a threshold. If it exceeds it, the receiver says 1, otherwise it says that message 2 was sent. Now what is this quantity? This is the analog of the matched filter output for the Poisson case. Is the analog in the Poisson domain of the matched filter output in the Gaussian case. So in the Gaussian case, the output of the matched filter tuned to signal x of t is this correlation. The role is played in the Poisson case by this quantity. So we look at each of the occurrence times from t1 through tn, compute the value of the transmitted signal at those event occurrence times divided by lambda 0, the dark current rate. We can think of this as the signal to noise ratio. This is 1 plus the signal to noise ratio, natural log, and this is summed over all the event occurrence times. Now this quantity is computed for each of the 2 signals, and then the difference is compared with this threshold. So in fact, if you look at the output of the Poisson channel y of t as a sequence of ideal Dirac impulses, then this quantity here, this here, is in fact the output of a matched filter whose impulse response can be written down. Okay, so this is how the optical match filter is an analog of the match filter in the Gaussian case. Now the other thing is that the error performance, unlike in the additive wide Gaussian noise case, is not determined by the L2 distance or by any other distance between x1 and x2. So in this way, the problem of detecting over a Poisson channel is different in its structure from what it is for the additive wide Gaussian noise channel. Okay, then following the work of Bart David, sure.
That's also reminiscent of like a signal-to-noise ratio, but directly just in the count business, right?
This is exactly right. So you see, that's right, because if you look at this, then you bring the lambda 0 here, this becomes x plus lambda 0, so that's the rate of the Poisson process when the signal is there, right, divided by lambda 0, which is just the dark current when there's no signal. That's exactly what it is. Now, following the work of Bart David, there was a rich body of literature that developed in problems of detection, estimation, and filtering for the Poisson channel. And this is a partial listing of some of the work. A rich compendium of the progress until 1999 can be found in this survey paper by Sergio Verdu. It's called Poisson Communication Theory, and it was in honor of Israel Bart David. And there has been a subsequent body of literature that has developed since then. So now we get to the third section of the talk, which is the first main topic of this talk, which is the Shannon capacity of a Poisson channel. Now, in a way, if we look at the Shannon capacity problem, it can be viewed as a detection problem in which we are not trying to detect between two signals, but between m signals, let's say. And the larger the number of signals, the better off we are. But we do have some control now. We have control over the manner in which the transmitted signals are chosen. And we also have control over the time duration over which the signals are going to be sent. In fact, we can make this time duration of the signals as large as we wish. And the idea is to find out what is the largest number of signals we can send over the Poisson channel and tell them apart at the receiver with error probability going to 0. So that is in a nutshell, that's the Shannon capacity problem. So getting to the setting of the Poisson channel, here is the setting for looking at the capacity problem. There are capital W messages. Again, W is not a random variable. Little w is a generic message. We are going to look at a single user channel model. The message little w goes into the encoder. It's mapped by the encoder into a code word. In this case, it's a code waveform. The code waveform, of course, depends on the message. It's a time signal. This is the input to the Poisson channel, which has this dark current rate. The rate lambda of t is the sum of the transmitted signal and lambda 0. And the output of the channel is a Poisson counting process with rate lambda of t, which is a deterministic quantity. Lambda of t is deterministic. It depends on the message. And the decoder has to form a good estimate of the message that was sent. So this is the basic problem. The transmitted code words will be required to satisfy both peak and average power constraints. And again, these are called power constraints because they are constraints imposed on x of t. But it's the instantaneous power of the optical signal that is proportional to x of t, and hence the nomenclature. I'll talk about these constraints shortly. Now, we make two simplifying assumptions. They also happen to be serious shortcomings of this model. The first is that this is a continuous time model, so we should be looking at bandwidth constraints. Instead, we are going to assume that bandwidth limitations associated with the transmitter and receiver devices and also the optical medium are ignored. Okay. The second is that we're going to assume that the intensity of the background radiation is constant, namely this lambda 0. What this means is that we're ignoring the effects of infrared light and visible background light, and assuming that the dominant source of background noise is the dark current. Now, this leads to a simplified model, but it also enables exact calculations, as you will see. This is the Poisson channel model. for this problem. One of the messages goes in, and then this is the code waveform corresponding to it. The output is y of t, which is a Poisson counting process of rate lambda of t, which depends on the message. It's a time signal plus lambda 0. All the signals are sent and received over a time interval 0 to cap t. Now, the transmitted code words are required to satisfy two sets of constraints. One is a peak constraint, peak set of constraints, where each of the waveforms must be non-negative, as you saw before, and is bounded above. Each of the waveforms is bounded above by has an upper bound or a peak power constraint. So what this means is that the laser cannot be pulsed at more than a certain peak power. That's what this constraint says. The second says that if you look at the average power, it must be bounded above by sigma A. What this says in effect is that if you look at the average power and divided by A, which is the peak power, this ratio is called the duty cycle of the signal or the duty cycle of the laser. The duty cycle of the laser can be no more than sigma, therefore sigma is some number between 0 and 1. So it constrains the duty cycle of the laser. So that means that the laser cannot remain on for long periods of time. So these are the two constraints that are imposed. And the question that the capacity problem asks, or the questions, are the following. So first question, what is the capacity of the Poisson fading channel under the peak and average transmit power constraints? Now, what is channel capacity? For those of you who have not seen it before, it is the largest rate. And how is the rate defined? Well, capital W is the total number of messages. Take its natural log. That gives us nats of information. Normalized by T, the signaling duration. So this is the amount of information in nats per unit second that can be transmitted reliably over the channel, and for which there exist codes, by which I mean there exist codes consisting of an encoder and a decoder, such that the probability of decoding error tends to 0 as the signaling duration tends to infinity. So this is the question. Second, what are properties of the optimum capacity achieving transmission strategies? So these are the two sets of questions we try to answer. The answer to this capacity question is given by this expression. Now, I'll try to explain this expression. First, if we look at an additive wide Gaussian noise channel, let's say the discrete time version, then we know that the capacity is half log 1 plus the signal to noise ratio. The role of the log function for the Gaussian case has its counterpart in the Poisson channel case, and that counterpart is the zeta function, which is a function of two variables x and y. So it's x plus y ln x plus y minus y ln y. This function is non-negative and has some other nice properties. The channel capacity is given by this expression here. So what does this mean? We know that in most of these models, the channel capacity is the mutual information between the channel input x and the channel output y maximized with respect to the channel input. Now, this represents the mutual information between the input x and the output y, and I put it within quotes because we are actually looking at the mutual information between input and output processes normalized by time, whereas this is a shorthand notation which uses single short random variables. So I put it in quotes this way. This mutual information equals the differential entropy of the output y minus the conditional differential entropy of the output y given the input x. And this has to be maximized with respect to the input random variable or the input distribution x of x. Now, x is the input. It will satisfy two constraints, the peak power constraint and the average power constraint. The peak power constraint says that, well, first, x has to be non-negative. We saw that before. And x is bounded above by a. So that's the peak power constraint. The average power constraint says that the expected value of x is no bigger than sigma a. So the average power constraint on the signals is translated into a moment constraint on x. And in fact, it is shown that this capacity is achieved by IID random variables which take only two values, either the lower value 0 or the peak allowed value a. Just binary signaling. And what does that mean? It means that if I look at the expected value of x, this is simply equal to A times the probability that X equal to A. Right? Because X takes the values only 0 or A. That's shown. And therefore, how do we... I can get rid of this.
Yeah.
Okay.
You have to put it back. You have to put back the pens.
Aha. Put back which pen? Where did I...
Oh, I think you used the wrong pen.
Aha.
Yeah. Yeah, that's not... Yeah.
I used the wrong pen, yeah. Yeah. Sorry about that. Now, maybe more to the point, how do I get it done? Let's see.
Just click it.
Yeah, there it is, yeah. Okay, we are where we are. This reminds me, Brian, you might recall this, Rudy Alswida. He was giving a talk using transparencies, and somebody asked him a question, and he wanted to give an answer. So rather than go to the board, he tried to write on the transparencies. And he got excited after a while, and he pushed away the transparencies and wrote on the glass. For the rest of the talk, it was projected on... I hope it's not distracting.
No, I think that'll come up.
It'll come up, okay. Yeah, so therefore, this constraint is simply a constraint that A times the probability X equal to A is bounded above by sigma times A, which means that the probability that X takes its maximum value A is bounded above by sigma. Now, the probability that X equal to A is called the operational duty cycle. It's simply the proportion of time when X takes its peak value. The laser is on. So therefore, the constraint is actually on the operational duty cycle. And let's call the operational duty cycle to be mu. So this expression simply is a constraint on the operational duty cycle, namely mu, which is the probability that X equal to A. Therefore, if you take this expression and compute it, it can be expressed in terms of the zeta function, and it is given by this expression, which is maximized overall mu lying between 0 and sigma. And so this is the formula for the capacity. The optical channel capacity problem has seen a lot of work, and Karbanov proved the capacity of the optical channel with the peak power constraints but without the average power constraints. And then Mark Davis gave this formula with the inclusion of the average power constraints. And both these approaches used martingale arguments. And then this formula was then given in 88 by R.N. Weiner, who used a completely different approach. And Weiner's approach was the following. What he said was, we take this Poisson channel, which is a continuous time channel, and we make a discrete memoryless channel approximation for it. Now, what is this DMC approximation? Take the time interval from 0 to capital T and divide it into tiny subintervals. Okay, and look at the channel input and output during these subintervals. The input to the channel is going to be binary valued, 0 or A. Therefore, the input to the channel is discrete. If we look at the output of a Poisson channel, any Poisson process, and if you look at a sufficiently small time interval, then the probability that there is no occurrence of an event is significant. The probability there is one occurrence is also significant. The probability of occurrence of 2 or more events is negligible. So in effect, by taking the time interval to be very small, the time slots, after dividing 0 through capital T, the output of the channel looks binary, 0 or 1. And this is the approximation that he made, computed the capacity, and then took the limit as the number of slots go to infinity. And so that was the idea. And again, what he showed was that binary 0A valued signaling with arbitrary fast intertransition times. So the idea was that you had signals, input signals, that took on the values 0 or A, but jumped from 0 through A to A arbitrarily fast. So the intertransition times were very rapid. Therefore, clearly, these signals are infinite bandwidth signals. They are the ones that attain capacity. And as I explained just now, the output alphabet is effectively binary valued. Now, Weiner did something in his work which is quite remarkable. He found the reliability function or the error exponent of the Poisson channel. What is this? This is the best exponential rate at which the probability of a receiver error tends to 0 as the signaling duration capital T tends to infinity. This error exponent in general is not known for any channel for rates less than the capacity, and the Poisson channel is one of those rare instances for which the error exponent is known for all rates less than capacity. So I'd like to draw an analogy between the optical channel and the radio frequency channel. Now, let's compare with the additive wide Gaussian noise channel. This is a discrete time channel, whereas the Poisson channel is a continuous time channel. But nonetheless, for the Gaussian channel, the output at any time instant y is the sum of the input x and additive Gaussian noise n, where n is a Gaussian random variable with mean 0 and variance sigma square. And therefore, the capacity is going to be the maximum of this mutual information, subject to the constraint that the input x is constrained in its second moment to be no larger than p. This models an energy constraint on the signals that are used. So the expectation of x squared should be less than or equal to p. This mutual information is again the differential entropy of the output minus the conditional entropy of the output given the input. But this conditional entropy is simply the entropy of the noise and has nothing to do with the input. This is maximized over all inputs which satisfy this constraint. Now, if we set the expectation of x squared to be mu, then this expression is simply this expression, half log 1 plus mu by sigma square, maximized over all values of mu which are less than or equal to p, and the answer is simply half log 1 plus p by sigma square. And this maximum is attained by a Gaussian input with mean 0 and variance equal to p. Now, there are two things to be noted here. For the additive wide Gaussian noise channel, when the signals are electrical, mu is the expectation of x squared, whereas in the optical case, mu is equal to the expected value of x. So that's one difference. But more significantly, when we look at the Gaussian channel, this conditional entropy of y given x is simply the entropy of the noise, and it doesn't depend on the input. And so it does not play a role in the optimization problem when we try to find the optimum value of mu. By contrast, when you look at the optical channel, this conditional entropy of y given x is related to the input through its mean mu. And it is this dependence of the second term on mu which makes the computation of the optimum duty cycle mu or mu star difficult and leads to a correspondingly complicated expression for the capacity. So this is why the optical channel in its form is significantly different. The optical channel capacity is significantly different from that of the Gaussian, from its Gaussian counterpart. All right, so as I said before, Weiner, one of the big contributions in his work was also to find the error exponent for the optical channel. And in fact, he gave a constructive scheme. And this is a very simple and a very elegant construction. And it could be useful in practice. So I wanted to show you, I wanted to discuss this construction that Weiner gave for attaining the error exponent of the Poisson channel. Now, what is this construction? We know that the capacity is achieved by a binary valued input where the probability that x equal to a is mu star. So this comes from a computation of the channel capacity. We know how to compute mu star. Now, we take mu star and form this rational approximation of it. So mu star, let's approximate it by k, an integer, divided by w, the total number of messages, where k is some integer between 1 and w. Then we construct this binary matrix which has as many rows as there are messages. So in this example, w equal to 5. There are 5 messages. So this matrix has 5 rows. It's a binary matrix. And the matrix is constructed so that each column has exactly k ones in it, where k comes from here. So the weight of every column in the matrix is going to be 2. So clearly there are going to be w choose k such distinct columns. In this particular example, k equal to 2, so there are 10 distinct columns. So we have a 5 by 10 matrix. Now, by virtue of the symmetry of this matrix, it's easy to see that the number of ones in every row is also the same. And in fact, the proportion of ones in every row is exactly equal to k by w, which is mu star. Okay. Then the code waveforms are constructed as follows. So let's say we want to construct a code waveform corresponding to the second message, which would correspond to the second row here. This is how it's done. Take the time interval from 0 through capital T and divide it into as many sub-intervals as there are columns in this matrix. So that's T divided by W choose K, which is T by 10 in this example. Then look at the second row, because we want a code waveform for the second message. Every time we see a 1, we put an A in the corresponding sub-interval. And every time we see a 0, we put a 0 here. So this is the code waveform that corresponds to the second message. All the code waveforms can be constructed for all the messages. And it's easy to see that these code waveforms will satisfy both the peak and the average power constraints. And more remarkably, if we look at any two waveforms pairwise and look at the joint empirical distribution, these two waveforms will appear as though they were generated by independent signals. And furthermore, these signals will have the same properties as those that attain capacity. So this is a very simple and clever construction, and I wonder if it has use in some applications. So that is worth investigating. Okay, so we come to the last segment of the talk, which is the Poisson fading channel. So first question is, what is optical fading? Temperature variations in the troposphere, which is the lowest layer of the atmosphere, which stretches from about 7 kilometers at the poles to about 20 kilometers in the tropical areas. There are temperature variations, and these are due to atmospheric turbulence. So you have pockets of warm and cold air that move around randomly. And these random movements of air give rise to random variations in the refractive index of air at optical wavelengths. These variations in refractive index are also caused by obscuration due to snow, rain, fog, smog, and so on. In turn, these random variations cause random fluctuations in the intensity of an optical beam as it propagates through the atmosphere. And this phenomenon is called optical fading. It's also known as scintillation. There are two features of the fade that are relevant. First is that these fluctuations routinely exceed 10 dB, I should have said 10 dB per kilometer. And so such fading can give rise to a significant increase in link and error probability, and therefore must be combated. The second feature is that these fluctuations have a coherence time over which they remain constant, more or less constant, of about 1 to 10 milliseconds. So this optical fade is in fact a slowly varying fade, a fact that can be exploited in improving communication performance. So like in the case of radiofrequency fading, there are two common techniques that are proposed for combating optical fading. The first one is to use estimates of the fade, it's also called the channel state information, or CSI, at both the transmitter and the receiver in order to improve communication performance. The second technique is to have spatial diversity in the form of multiple transmit and receive apertures, for instance, an array of LEDs or lasers at the transmitter. So the basic model that corresponds to the optical fading channel is the following. It looks much like the picture that we saw earlier, except that there are some differences. The transmitted optical signal XO of T is of course the same as before. The received optical signal now undergoes a fade. Now this RO of T is no longer the transmitted optical signal, which was a deterministic quantity, but it's actually a process in time and space, is the product of the transmitted optical signal and a fade. It's a multiplicative effect, and the fade has both time and spatial components. And therefore, when this received optical signal goes through this device, what comes out is a time signal R of T, which is no longer a deterministic signal, which was equal to X of T as in the case when there was no fading. But in fact, R of T is approximately the product of the transmitted signal and a time-valued stochastic, a temporal stochastic process, S of T. Therefore, now y of t, the output of the direct detection device, is a Poisson counting process with a rate lambda of t, which is now a stochastic process. And this capital lambda of t is related to the transmitted signal x of t, the temporal fade s of t, and the dark current lambda 0. And the question is, how do you communicate over such a system? So, by the way, this process y of t now is also referred to as a doubly stochastic point process or doubly stochastic Poisson process, because the rate process capital lambda of t is itself a stochastic process, unlike in the case when there was no fade. So the setting in which we examine this problem is one which has a single user, multiple input, multiple output channel model with multiple transmit and receive apertures. So in this setting, we propose a block fading channel model with channel state information at the transmitter and receiver. And by what I mean by this is the following. Because it's a slowly varying fade, and the fade remains constant over coherence time intervals of 1 to 10 milliseconds, we take the channel fade process to be a random process, but which is piecewise constant. And it remains piecewise constant over these coherence time intervals of 1 to 10 milliseconds. Okay? And then it varies across these different coherence time intervals in an IID fashion, independent and identically distributed, and we assume that we know the distribution. The second feature is that different levels of channel state information are provided to the transmitter, and we have perfect channel state information at the receiver. What this means is the following. If you have a modulation rate of, let's say, 1 gigabits per second, this is the information rate. During a time interval of 1 to 10 milliseconds during which the fade remains constant, during a coherence period, 1 to 10 megabits are transmitted and received by the sender and the receiver respectively. Now the receiver can take a negligible fraction of these bits and form a good estimate of the prevailing channel fade, which is the reason for assuming, or the rationale for assuming, that the receiver has perfect channel state information. Then, depending on the availability of a feedback link and the amount of delay that can be tolerated, some of this information can be fed back to the transmitter during the same fade interval, and the transmitter can use this information adaptively to do power control. And that is the problem setting we are going to examine next. Now, I should say that the study of the Poisson channel with or without fading, without or with fading, has had a long and rich history. And the problems that have been studied can be classified broadly into 3 groups. So the first is the direct detection photon channel without fading, the MIMO optical fading channel, and the optical infrared channel with Gaussian noise at the receiver. And these are some of the references, but this is far from a complete list. So the model that we are interested in is the following. This is a model with capital N transmit apertures and capital M receive apertures. So it's an N by M MIMO Poisson fading channel. The received signal Ym of t at the little mth receive aperture is going to be a Poisson counting process whose rate is given by this expression. We take the signal xn of t sent from the nth transmit aperture multiplied by the fade or the channel gain from the nth transmit aperture to the mth receive aperture, and then this is summed over all the transmit apertures, and then added to it is lambda 0 of m, which is the dark current rate at the nth receive aperture. Therefore, the received signal at the little mth receive aperture is a Poisson counting process whose rate is given by this expression. And for this model, the fade is viewed in this way. Typically, the fade process is taken to be an ergodic log normal process, and the correlation time is 1 to 10 milliseconds, during which the fading process remains more or less constant. And therefore, the model is a block fading channel model in which the channel coherence time, T sub c, plays a role. And in fact, the channel fade process is a matrix, right? It's an n by matrix. Now, this varies in time as a stochastic process, but because of the coherence times, we can view the process as a sequence because the process is piecewise constant, and the sequence is now indexed by k, namely the coherence time period. So that's what this says, that the fade process, actually the matrix is S of k. It's a matrix sequence, random sequence, which is taken to be IID with a known distribution. Now, in this setting, we are going to assume that the receiver has perfect channel state information. From a practical standpoint, this was reasoned just a few minutes ago. From a theoretical standpoint, it must be admitted that this assumption is crucial for the tractability of the calculations. So it's used in a big way. The transmitter channel state information, on the other hand, need not be perfect. It's defined in terms of some function h of the actual fade, where h can be any mapping. It's arbitrary, so for instance, if h is a constant, then the transmitter has no channel state information. If h is the identity mapping, then the transmitter has full channel state information. Okay. The transmitted code words again must satisfy peak and average power constraints. This is the peak constraint here. Each of the signals for every message must lie between 0 and a sub n. A sub n is the peak power constraint at the transmitter n. Each of the code waveforms is a function of the message. It's a time signal, but it also depends on the channel state information, which is modeled by you up to and including that point in time. And similarly, there's an average power constraint as well. In this setting, these are the following questions we ask. What is the capacity of the MIMO Poisson fading channel subject to these constraints? What are the properties of the optimum capacity achieving strategies? And what are the effects of channel state information at the transmitter? Can the performance improve? And as you see, all these questions are framed in double question marks, so they all remain open. However, a special case can be solved where we have a single input and a single output, one transmit aperture, one receive aperture, and I'll present this result now. But as you'll see, the capacity formula for the single input, single output Poisson fading channel model is more complicated than the Poisson channel capacity without any fading. So the model of interest is the following. The input to the channel is x of t, the transmitted signal. The output is a Poisson counting process with rate capital lambda of t, which is a stochastic process, which equals the transmitted signal multiplied by the value of the fade during a coherence time interval plus lambda 0. The transmitter channel state information is now given by UK. For each, this k indexes the coherence time periods. It is some function of the actual fade, while the receiver has access to perfect channel state information. So this is the model we are looking at. The capacity for this model is given by this expression. So let me explain this, and I'll tell you how this formula comes into being. Now the capacity between the capacity of the channel is no longer the mutual information between the input and the output, because there is channel fade information involved, and the receiver knows the channel fade. So the mutual information is replaced by the conditional mutual information, and therefore the quantity to be maximized is the conditional mutual information between the input x and the output y conditioned on the channel fade s. This, of course, this conditional mutual information is the difference of the conditional entropy of the output given the fade minus the conditional entropy of the output given the input and the fade. This has to be maximized over the input, but the input now has access to channel state information which was modeled by you. Therefore, when we maximize the input, we don't maximize it with respect to the distribution of x, but rather with respect to the conditional distribution of x given you. Conditional distribution of x given you. And the input x must satisfy peak and average power constraints, so x must be bounded below by 0 and bounded above by a, just as before. And secondly, the expected value of x must be bounded above by sigma times a. But the expected value of x can be written as the conditional expectation of x given u, and then you take another expectation by iterated conditioning. So this must be bounded about by sigma a. So now what's going on is that it can be shown again that binary valued signals will attain capacity. And now if binary valued signals attain capacity, then and we are interested in the duty cycle, right? So when there was no fading, we wanted to maximize the mutual information as a function of the expected value of x, which, because of the fact that the signal took the values only 0 and a, was equal to the probability that x equal to a, which was called the duty cycle mu. Now the duty cycle will also depend on the channel state information at the transmitter. So it is not mu, but it is mu of u, over which we have to optimize, and the expected value of mu of u should be bounded above by sigma. And this mu of u is the power control in the optical case. So how do you control the duty cycle as a function of the channel state information? That's the analog of power control in the optical case. So again, as I said, the achievability can be, the capacity is achieved by binary valued signaling with arbitrary fast intertransition times. And now the duty cycle is a conditional duty cycle because it depends on the value of the channel state information at the transmitter, namely u. So it's mu of u. And this mu of u is simply the conditional probability that x takes the value a conditioned on the channel state information little u. And this plays the role of the power control. And it must satisfy this constraint, of course. And in fact, capacity is achieved by coding across several coherence intervals. So now it remains to find the optimum mu of u, namely the optimum conditional duty cycle. And I just wanted to make a comment in this case that the capacity does not depend on the coherence time, T sub c, which is a consequence of the fact that the receiver has access to perfect channel state information. If this were not the case, then the capacity would in fact depend on the coherence time. So now it remains to compute the optimum power control law, mu star of u. Now, it's good to draw an analogy with the case of radio frequency fading. Right? And here is the analogy. If I look at a radio frequency fading channel with additive Gaussian noise channel, now this is a discrete time model, but nonetheless, in the work of Goldsmith and Varaya, the output of the channel is the product of the input x and the radio frequency fade s plus additive white Gaussian noise of mean 0 and variance sigma square. Right? Now in this case, the capacity again is the conditional mutual information between the input and the output conditioned on the channel fade. Now this is maximized with respect to an energy constraint on the input. That energy constraint says that the expected value of mu of u, where mu, the power control in the radio frequency case, mu of u is the conditional expectation of x square conditioned on u, not the conditional expectation of x conditioned on u, but the conditional expectation of x square conditioned on u. And that must not exceed p. And if this problem is solved, this is the maximum of this difference between conditional entropies, maximized as a function of the power control law. And we know that this is attained by the water pouring or the inverse water filling power control law. And the analog in the optical case is optimization with respect to this mu, which is, I'll be done in a minute more, mu, which is simply the probability that x takes its peak value, namely condition on the channel fade information at the transmitter u, and this is the conditional duty cycle. Well, let me just say that, of course, this slide is very forbidding, but it just makes 2 points. So one is that you can actually compute mu star, the optimum power control law, by solving this equation. And the second is that the optimum power control law actually falls into one of two regimes. The first is where the average power constraint parameter sigma is large enough so that the average power constraint is inactive, and this is a case where the average power constraint is active. And in fact, maybe this picture is more useful. This is a picture that depicts the optimum power control law. On the x-axis is the value of the channel fade S. On the y-axis is the optimum value of the power control law mu star of S. So it's a probability between 0 and 1. And this is the optimum power control law when the transmitter 2 is assumed to have perfect channel state information, namely H is the identity function. And the fade is log normal, and the signal to noise ratio, which is defined as the ratio of the peak power to the dark current range, is taken to be 1. So there are two zones. This is the zone where the average power constraint is active. And what you see is that when the fade value is low, so which means the fade is debilitating, then the transmitter must not send, because the power control law says that the probability mu of S is 0. This is very much like, at least in spirit, it's like what happens in the radio frequency channel case. When the fade is debilitating, the transmitter doesn't send. As the value of the fade becomes more favorable, then the power control law says that you transmit, and the probability of being in the on state approaches an asymptotic value. This is the zone in which the average power control, the average power constraint is inactive. And here we observe the following phenomenon. Even when the fade is terrible, so fade is debilitating, the power control law says you still transmit. Okay? This is very much unlike the radio frequency case. And so the power control law says start transmitting at a probability of 0.5, and as the fade becomes more favorable, this tends to an asymptotic value. Therefore, in the optical channel case, there are two forms of behavior. In one zone where the average power constraint is active, the results are the power control law is in the spirit of radio frequency fading, but in the zone where the average power constraint is not active, then the behavior is quite different from what it is in the case of the radio frequency channel. So I will skip a few slides and come to the end with some open problems and new ideas. So why is it that the general problem of multiple input, multiple output, of the multiple input, multiple output model, why is it unresolved? It is due to the fact that the optimum power control laws at the multiple transmit apertures cannot be precisely characterized. And the reason for that is that at optimality, the power control laws at the different transmitters are correlated. And it is the precise nature of this correlation that is not characterized. And as a consequence, we don't have a general formula for the capacity of the MIMO channel. Now, this is very much in contrast with what we have in the radio frequency fading case with Gaussian noise, where there is this nice result of Emra-Teletas which says that the capacity scales as the minimum of the number of transmit and receive antennas compared with the single antenna case. There is no analogous result in the optical case. Secondly, the assumption that we have perfect information at the channel information at the receiver is not practical, and if we drop this assumption, then the capacity in fact can depend on the coherence time interval. And the last open issue is that we have assumed that signal is binary valued with arbitrarily fast intertransition times because there are no bandwidth constraints. But if explicit bandwidth constraints are imposed on the transmitted signals, then multi-level signaling may have to be considered. So if there are PhD students here who are looking for a rich and juicy set of problems that are difficult in a problem area that is going to become more significant, then you might consider looking at these problems, because new ideas are needed, and it would really be nice to have answers to some of these questions because they're going to become increasingly relevant. Thank you.
A couple of quick questions. Any questions?
So in the receiver for the optical channel, the receiver statistic had a sum of all the previous received signals.
Yeah.
Does that mean the output of the receiver depends on previously received signals, or it's just how the optimal receiver behaves?
When you say previous,
So we had like a sigma I equal to 1 to n, which is...
Oh, no, no, that was not the previous. Okay, so you're referring to... this, no. I think by the time I'm done, I'm going to destroy your system.
So somewhere in back.
It's somewhere here, right?
Right.
Maybe here. This is the one?
Right.
Yeah, so this is simply says if I look at any...
No. I think it was much more to the fact. When you're looking at the... when you're talking about the analog in the optical channel for the match receiver.
Yeah.
For the Poisson channel.
Yeah.
You had...
Oh, yeah. Okay, so you we had the sum... This is okay, right?
Yes.
I'm very nervous now here. I going from 1 through n,
Right.
ln of 1 plus x tj by lambda 0.
Right.
Right?
Right.
Huh. You do this for each signal and then take the difference. So this is simply the log of the signal to noise ratio at the event occurrence times, and you sum them up. So I going from 1 through n is simply it indexes the event occurrence times t1 through tn,
Right.
and then you compute this stuff.
So you're making this decision at nth time, is that?
Yeah, you look at all the events in during the time interval from 0 to n,
I see.
and then make the decision.
Okay, for item.
Yeah. And it's like finding the correlation, because you see you're correlating the transmitted signal, a transmitted signal with the received signal. And really, if you look at the output as a sequence of delta functions, direct delta functions, then this is the output of a linear filter whose impulse response we can write. Yeah.
So what kind of hall are we talking about? You were saying, for instance, these buildings to buildings and things like. What are we talking about here?
Yeah. So it also depends. So it depends on the laser, depends on the distance, and depends on the power available. Right. So for about 200 meters or so, lasers are being considered which operate at about 10 milliwatts. You need about 250 milliwatts for a kilometer, and up to a watt for 3 or 4 kilometers. So 3 or 4 kilometers would be one range. Now people are talking about larger ranges, but then you require a higher powered laser, and also the fade will increase, because the fade goes from anywhere from 0.2 dB to about 20 dB per kilometer, depending on the condition. So the longer the distance, the more acute the fade. But yes, at least until 3 or 4 at least for 3 or 4 kilometers, things are being envisaged right now.
But then isn't there any health hazard when you start basically?
Health hazard? Well, it's
Looking at a few
less than
dozens of watts of laser.
Never get in the way of a laser. No, they're fairly focused, so I'm not qualified to answer that question, but I would assume that it's
maybe the birds.
maybe the birds. Yeah, the birds. Yeah. Actually, you can use two lasers. Let's say one laser to clear a path, and the second to transmit. I'm just joking.
Yeah. Well, I mean, I think the what do they call it? Wang. I forget the name of the company, but the name of the company is WANG.
WANG. Yeah.
Wang Systems.
Yeah.
I think back in the 90s they were talking about something like this for the business community and things like that.
So you know, when I started doing my PhD work, there were some people who were interested in optical communication. So there was a main campus of Washington University where I was, and there was a medical school campus which was about 3 miles away. And there were some people who were trying to set up an optical link, a direct detection. So part of my excitement was to go to the medical school building, climb up through the attic to the rooftop, and it was quite a climb. and then try to make sure that we could acquire the beam coming from the source 3 miles away. And so these experiments had been tried out. I think in more recent times, people also considering things like this in shop floors, where you have robots moving around that are communicating using both radio frequency signals and also optical signals. So because the radio frequency spectrum gets very cluttered quickly. Of course, with the optical beam, there is a problem of acquisition, tracking and acquisition. So that's a challenge unto itself. But there are a number of very interesting problems. And the other question is, how do you flip back and forth between a radio frequency link and an optical link when you have both the options available? And you have fades on both links. So there must be a natural way to switch from one to the other. Of course, the optical one is the favored one if there's no significant fade. But there can be a fade or things get in the way, for instance. Then you must have some automated way of switching from one to the other. And that leads to a very nice problem. So Brian, you know the sum channel in information theory where you have parallel links. And so so if you have a parallel channel, it says you have 2 channels, and you can transmit on one or the other, but not on both. But this is better than transmitting on the better link, because by switching between the 2, you actually convey additional information. Now, I don't know if this is far-fetched in this case, but it's another angle to look at things from, in that just by switching between the 2 channels, you can convey some additional information. Whether it leads to meaningful gains or not, I don't know. There are many interesting problems, at least at the theoretical level. Abraham.
Yes, please.
So in the RF regime, MIMO communications tremendously increases the capacity. I understand in this case there's not a known scaling law, but is there some comparable significant boost in the capacity in this case?
So yes, there are some experiments that have been done which show that there is a significant improvement. But I would say that even in the single input and single output case, it's good to see if, first of all, fade information at the transmitter helps, right? If the signal to noise ratio is too low or the signal to noise ratio is too high, then transmitter fade information doesn't help, and this is what you would expect. Now, when you go to the intermediate range, if the average power constraint is active, then there can be a significant improvement in capacity. This is for the CISO case. Now, for the MIMO case, you would like to have similar analogies. So at least in the middle signal to noise ratio range, calculations show if you do the optimization numerically, then there is a significant improvement. In fact, in the MIMO case, some things are known. So we have results which show that if the fade matrix is a constant matrix, constant means it can have different components, but we know the values. Furthermore, so it's not random anymore. Everybody knows it. And the average power constraint parameter sigma is the same across all the transmit antenna. Then it can be shown that simultaneous on-off keying is optimal. So which means either all the apertures remain on or all of them are off. And this is also interesting because it provides the MIMO generalization of the optical fading, of the optical channel without fading. Because what it would mean is that if you had average power constraint sigma that was the same throughout, in the MIMO case, without fading, then all the transmit apertures would have to be on or off. Now, coming back to the fading channel, this is known, and some calculations for this setting show improvements. The second is if the fade is symmetric and isotropic, which means that all the peak power constraints A at the various transmit apertures and the average power constraint sigma at all the transmit apertures are the same, and all the elements of the fade matrix, they're all mutually independent and IID. Then using a number of tricks, we can find out what the optimum duty cycles are. And then in that case, some capacity calculations can be done to show that there are improvements. It's interesting the why in the MIMO case we cannot solve the general problem. So it turns out, as I said, that the optimum power control laws at the various transmit apertures are correlated. And the precise form of the correlation is the following. We have some structural understanding of the corresponding conditional duty cycles. So there's a duty cycle at each transmit aperture, right? And they constitute the power control laws. Now, the duty cycles have some sort of an ordering. You can order them, and the idea is that if you have a transmit aperture that is on, then all the other transmit apertures that have higher conditional duty cycles must also remain on. So that's a structural result. And therefore, that is known. Now, if you try to use, therefore it means that the conditional duty cycles at the different transmit apertures have to be ordered, let's say in increasing order. But when you do that, when you look at the mutual information formula for the capacity, which I sort of flashed through, you can write an expression, but you can't find the optimum conditional duty cycles. Because of this ordering, there's a permutation of the natural conditional duty cycles, and the mutual information expression now is no longer differentiable because of this permutation. And it is this that creates a difficulty in precisely characterizing the precise power control laws. But in some special cases, numerical computations do show that there are improvements. Sorry, it's a long-winded answer, but this is where things stand now. Yeah.
All right, let's thank our speakers.
Thank you.